Here's another example on how to graph rational functions and rational functions with holes. So in this case, this is my original function and I have already started factoring. So we can notice that 2x is both a common factor in both terms of my numerator, so I can factorize this as 2x times x minus 4. And also, x is a common factor in all terms in the denominator, so I can factorize an x. Because my denominator is not still in a linear term, I can factorize it even more. So, two numbers that multiplied give me 12 and that added give me minus 7. These factors are minus 4 and minus 3. So at this moment, we can identify that we have a common factor in both the denominator and the numerator. So we know we're going to have a whole defined by that factor. But remember to always simplify your function. And also, notice, I have an x in the numerator and an x in the denominator. So x equals 0 is going to be another factor. So if I simplify this function, I have 2 over x minus 3. So I am going to have a whole given by x equals 4 and x equals 0. Why equals 0? Because remember, you grab the entire factor. In this case, the factor is x minus 4. In this case, it's just x. You equate it to 0 and solve for x. The moment your factor is just x and you equate it to 0, there's nothing left to do. So we're going to have those two holes. Remember that holes are holes in the graph. So I have to find those holes through which my function passes. To do that, I'm going to evaluate the simplified function in these values. So f of 4 is 2 over 4 minus 3. So this is 2. So one coordinate for a whole is 4, 2. For the other one, we have f evaluated in 0. This is 2 over minus 3. So the other coordinate is in 0, minus 2/3. I'm going to plot those holes. So in 4, 2, there's going to be a hole. And the other hole is in 0, minus 2/3. So around here. Now, also notice that this means that both 4 and 0 are not included in the domain, okay? Now, once we're done with holes, we're going to proceed as usual. From the simplified function, we can find the vertical asymptotes. Because the only factor we have here is x equals minus 3, I equate it to 0, solve for x, and I know that those, or that, in this case, is going to be my vertical asymptote. So in x equals 3, I have a vertical asymptote. Then, my horizontal asymptote is found by identifying the degrees of the numerator and the denominator. In this case, the degree of the numerator is 0 because it's a constant polynomial. And the degree of the denominator is 1 because it's a linear function, meaning that the degree of the numerator is less than the degree of the denominator. Thus, the horizontal asymptote should be y equals 0. So I can graph the horizontal asymptote. Now, to find the x-intercept and y-intercept, we do the following. To find the x-intercept, remember that that is found by identifying the numerator and finding the zeros of that polynomial. But remember, when your numerator is a constant, we do not have x-intercepts, because this would mean we have to do something like this: numerator equated to 0, and 2 clearly is not the same as 0. So that is why we do not have an x-intercept. Now, to find the y-intercept, what we have to do is evaluate the function in 0. But careful, 0 is a whole, meaning that 0 is not in the domain, so we cannot evaluate the function. Thus, we do not have a y-intercept. So, the only thing I have on either left side or right side of my graph is the holes. So because I know that even though there's a hole, my function has to pass through there, the graph of my function should look like this. To make sure we're doing something right, we can always evaluate on both sides of the equation, of the vertical asymptote. On the right side, we already have a hole there that is useful to plot the graph. So let's evaluate the function in another value, like in 5. So if I evaluate the simplified function in 5, this is 2 over 5 minus 3, and this is 1. So my graph passes through the point 5, 1. So here I have 2 points through which my function is going to cross. So here's the right side of my graph. We can do the same on the left side. Let's choose a value on the left side of my vertical asymptote, for example 2. If I evaluate my function in 2, this is 2 over 2 minus 3, this is minus 1. So another point through which my function is going to pass is 2, minus 1. Oh, I had to evaluate in 2, minus 1. So my function is going to pass through this point, and it's going to pass through this point. So that is enough for me to identify the behavior of the graph.